hello and welcome. I'm Becker and I will talk about the effectiveness of control flow integrity in practice. So you can see on the slides also my awesome co-authors, Jiska, Classen, and Matthias, Hollick, and I'm from the TU Darmstadt University in Germany. So I think we had this already, but let's talk about why do we need another memory mitigation scheme? After all, memory corruption is a solved problem, right? So now my take on that, if you look at the top 10 known exploited vulnerabilities in 2023, you can see that 46% of those really exploited vulnerabilities were actually memory corruption associated, and only then the typical other security problems such as improper input validation and so on came up. So what we can see here is that memory corruption is not a solved problem, but rather a persistent problem. And even though we have all those fancy mitigations, in the end we still end up not using them in practice, and we have these long-standing issues as a consequence. So why is CFI a solution that might help here? CFI, as already somehow mentioned by the previous presenter, prevents exploitation of memory safety bugs by inhibiting control flow deviations. What's really important here is that it does not prevent the original bug. So you still have your buffer override or buffer overflow or whatever, but it prevents you from gaining code execution by control flow hijacking. And why is this nice? So first of all, you can apply this to your existing code base. You don't need to rewrite everything in Rust. You can just basically flip some compiler switch and suddenly you have this protected binary. So this really makes it low effort to add this to your existing projects. Secondly, you have industry-ready and really working CFI implementations, for example, in the LLVM compiler framework or in the Microsoft world as part of the Microsoft Visual C compilers. And also what's really nice about it is that it assumes a really strong attacker model because it needs to defend against an attacker that has arbitrary read, arbitrary write capabilities, and can break ASLR and perform arbitrary computations on some server backend. So this makes it really a real-world attacker model and therefore can provide adequate protection against such attackers. So how does CFI actually work? So this will be based on the LLVM CFI scheme because we will need this for the second half of the talk, but the same principles apply also to some other schemes. So basically, if you have some function pointer and some valid call targets for this function pointer, which might be A, B, and C in this case, and you have this typical attacker who wants to divert the control flow to some other node D, which might be, for example, the system function or something other which is somewhat interesting for them. And what CFI now does is to basically impose a policy to restrict allowed flows here. And this policy can, for example, be type-based. For example, in LVM, it follows the type system. But you can also imagine some other policy approaches that are, for example, based on the control flow graph of the program and to limit then these flows. So how does this actually work in practice? So if you have some function pointer and you have a call to this function pointer, then your compiler puts an inline fast check there. And this inline fast check is module local. So this basically only checks if this address is of the expected type in the current program. And how is this done? By just having a big table where all the addresses of a certain type are stored. And then you can just look it up there and see if this is a good known destination. But this only works for local stuff. And we also need to do cross-module calls. And for those, you have the fallback to this CFI slow path function, which takes the expected type of this function pointer and the address of the pointer and passes this to the module CFI check function. This is a function that is exported by the module if it's CFI protected. And since this is part of the foreign module, it knows about all the type and address mappings in this module. So now this is created during compilation time, and then now this module can say, okay, I know that this function pointer and this type is a known location in my program, and else it can say, no, this is not something that this is not a valid pair, and then we can terminate the program and prevent exploitation. Also, you usually only do this for forward edge protection, but if you also want to protect your backward edges, you use shadow stacks for that, but I won't go into those in this talk for timing reasons. Next up is the notion of equivalence classes, which are important in this context. So what are equivalence classes? if you have, again, some function pointer, and you assign this some kind of class, which is basically the valid destinations that belong to this pointer, which might, for example, be just a type of this pointer, then you can construct a class of all valid destinations that have the same, like in this case, for example, type compatibility. And then you can say, okay, all calls to this class are fine, and if you have some other classes, then calls would be prohibited. And you can have basically an arbitrary number of these classes, as many as you want, depending on the scheme. If you had now some other pointer, then, for example, the calls to this lower class would be permitted, but not to the other one, and so on. And this is also interesting because you usually categorize CFI schemes in the number of equivalence classes that they support. Because if the number of equivalence class sizes is fixed, you call this usually a coarse-grained scheme, and you usually support not so many, like a few dozens different classes. And also, if you have a program-dependent number of equivalence classes, you call this a fine-grained scheme. This is much better because then you can have as many classes as you need to get the precision that you want. For example, if you have a type-based scheme, that would be an example of a fine-grained scheme because you can have as many types as you want, and you can get new classes by declaring new types. So in our work, we were interested in looking how these schemes are actually applied in the industry, because there are many academic solutions and proposals and different analyses of what works and what does not. But we were interested in seeing how this then translates to the industry. And so for that, basically, you can look at how approaches are usually look like. And in academia, you have these compiler-based approaches that I introduced earlier, but you also have instrumentation or binary rewriting-based approaches, which is kind of interesting because there you don't even need the source code. You just have some binary, you drop it in your scheme, and then you get a protected binary out of it. But this relies on heavy binary analysis and binary rewriting, and as we heard yesterday, is certainly undecidable. So this is kind of error-prone, and you don't really want your CFI scheme to mess up your program semantics and then in production run into some troubles with that. So that's basically why you don't really see these kind of approaches in the industry. Basically, all major schemes are just compiler-based. Next up, there's this question of granularity. If you look at the academic side, you have usually these coarse-grained schemes, a few, mostly the older schemes. Then you have the more recent fine-grained schemes with different kind of approaches. And what's also really interesting in academia is that you now recently have works in the area of context-sensitive CFI. Basically, there the idea is that the class of a pointer might change during its lifetime. For example, if some pointer should only be valid in a certain program state, then you need some kind of context sensitivity to basically track this and update the expected label. If you look at the industry, you basically only, for software-based schemes, you only see coarse or fine-grained schemes. There are no context-sensitive schemes yet. And if you look at hardware-based schemes, it's even worse because most of them are only fine-grained by design. With that being said, let's see. Academic schemes are therefore really promising because they have much better security guarantees, but they are not really often adopted in practice later. And something interesting that you can also see there is if you look at the few exceptions of schemes that are actually adopted by industry, is that authors of these papers tend to have really strong industry ties already. So if you look at the names, you see, for example, Google, 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 and then you see, okay, it was merged upstream later in LLVM, and you really see that there was incentive to get those schemes into practice already. While sometimes in more academic schemes, it's all about getting the novel idea out, writing this paper, getting nice results, but then maintaining these solutions takes a lot of effort. Getting these patches applied upstream takes a lot of effort. Let's take, for the basically remainder of this talk, take a closer look on the CFI on Android and see how it works there. This is just one part of our paper, but if you're interested in more, I need to delegate this to the paper because I only have limited time here. And so basically, Android is interesting because it supports a combination of different CFI schemes. On the one hand, it uses LLVM CFI for forward edge protection, so this is what we already covered. Then it has support for the LLVM shadow stack, but it's barely used anywhere, so I won't go into detail here. Then it also has support for the pointer authentication scheme by ARM, which is basically used to protect backward edge control flow transfers. To basically study the distribution and coverage of CFI on Android, we built an analysis pipeline to get more information on that. And the basic idea here is that we have a lot of firmware archives which we can extract and mount. And now we can iterate through these file systems and extract all the ELF files there, which we can then use for further analysis. So the first thing that we can do there is to perform some feature extraction to kind of check out what kind of ELF file is this. So the first thing that we want to know is the file type. We check for Rust files, kernel objects, ahead of time compiled code, and shared objects. The first, like the Rust-based files and the ahead of time compiled files are interesting because they basically are never CFI protected. At the time of writing, Rust was getting CFI support, but it was not there yet. So on Android, there are no Rust-protected binaries that use CFI. Also, this ahead-of-time compiled code for like Java-optimized code is also never CFI compiled. So we have to exclude them to get basically a fair picture. Also, we looked at files to detect whether they use pointer authentication and use shadow stack to basically include this later in our analyzers. And we then take these kind of features and put them in some database for later query. Also, we perform constant propagation, and to explain it a little bit, you can recall that we use the CFI slow path function because this is used to check cross-module calls. And because it's always there if there is some indirect call that is protected, we can look for this function to find protected indirect call sites. And what's also nice is that it takes two arguments, which is the type ID and the function pointer. And by propagating the constants, we can figure out what kind of type ID is used in this call site. So this means we not only have protected call sites, but also their associated type classes, which means that we can later reconstruct what kind of classes are reachable from different parts of the program. We also store these protected indirect calls in our database. Second, we can, and there use symbolic execution. Again, with Anger, we had this previously this morning already, because the CFI check is a really excellent target for that, because it takes the type ID and the function pointer, and it does not rely on any global state whatsoever. So and it also only uses really basic arithmetic instructions to check these input pairs. So this is basically a really good fit for symbolic execution, and you can then use this to symbolically execute the CFI check function and get out pairs of function addresses and their associated call targets. And this means basically we can now say, okay, here are functions and they have this and this type in our scheme. This is also quite interesting because you can use this for two other purposes. One of them is if you try to write an exploit for a CFI protected binary, you can then look up what are available targets for this kind of type. For example, if you have some pointer override and you know this pointer override has this supposed type, then you can use this approach to figure out in all of my shared objects what kind of valid targets are there that might be unintended and might lead to some security issues. In addition, you can also use this for program analysis because this basically gives away where functions start and also their type, even though this type is a hash, so you need to build some lookup table of common types to basically then figure out what the real type of this target is. With that being said, let's look at how the Android CFI coverage looks like. So this is, the following will be the graph for the generic system image, which is basically a more or less pure Android open source project build without vendor-specific stuff. In our paper, you can also find data on specific vendor builds from different Android devices. And what you can see here is that you, like the orange one is the unprotected libraries, the red ones are unprotected binaries, and the two blue ones are protected libraries and protected binaries, respectively. And as you can see, there is a lot of orange. And now you might say, OK, it's unprotected libraries. How bad can it be? And for that, we basically have to discuss what unprotected modules in LLVM CFI mean with regards to security guarantees. And for that, we call that CFI slow path is used to then figure out the correct CFI check function to call and to then check this call there. But what if the module is not protected, which is the case for these unprotected libraries? Well, you don't know anything about this module, so you can't perform any checks. So in this case, you will just say, OK, the call, it's fine, I can't check it, it will be valid. What does this mean? This means that every single gadget that you have in these modules is reachable, and not only reachable by specific pointers, but by all of them. So if you look at the equivalence classes again, this means that you add basically every single byte in this unprotected module that is executable. You add every single byte as a valid target in your equivalence class, and to every equivalence class. So this means basically a lot of additional choices for the attacker, and as you might be aware, in like large libraries such as libc, there is enough gadgets there already, so you don't even need anything else. And spoiler alert, on Android, the libc is not CFI protected, and it's basically loaded by almost every binary. So yeah, not so good. Also, what's kind of interesting is that you can look at the CFI coverage over time, and here in blue and orange, you see the LLVM-based forward edge protection, and in red and green, you see the pointer authentication-based protection. And what you can see here is that even though it got introduced with Android 10 or 9 already, I think, it didn't really change over time. So even though it slightly fluctuated, the CFI deployment got not extended further and seems to kind of stagnate there. With point authentication, you can see that it went up and kind of is improving, but you can also see that it's still only at like 40% global coverage, which is also not ideal. Next up, you can also visualize equivalence class size distributions to figure out what usually your protection level looks like. And for the generic system image, again, this looks like this. So what you can see here is on the x-axis the class size, and on the y-axis the number of occurrences. And this is over all the files that are protected on the GS14. And what you can see here, I think the scales are a little bit small to read, I'm sorry about that, that basically the single equivalent classes are really, really common, while larger ones are really, really infrequent, which is kind of nice. But there is a gotcha here, and this is without dependencies. So usually if you, I mean, it would not make sense to have single element equivalence class sizes, because then you would not use dynamic function pointers or vtables at all, right? So if you also consider dependencies, which again we can figure out by looking at the CFI slow path protected call sites, it looks more like this. And what you can see here is all protected files that have CFI slow path calls, independent of whether they are binaries or libraries. And you can see that here the distribution looks a little bit more uniform and more tending also to higher element equivalence classes, which is not so ideal. But this basically can help you in figuring out what the kind of the profile of your application looks like, in addition to the aforementioned more specific queries that you can do where you look at how exactly, what kind of targets are available. And with this, I kind of want to go to my takeaways and conclude my talk. So the first is that there is like a really large gap between schemes that we have in practice and in academia. And while this might be to all the aforementioned issues that you have when trying to get these schemes out, this is kind of sad to see. Also, you have some really big issues with an incomplete rollout, especially on Android, where you basically lose all your security guarantees by not fully rolling out your scheme, which is also, I think, a typical problem, because we saw this in an earlier talk with regards to stack canaries or other security mechanisms. And I think at this point it's just like a reoccurring theme that like mitigations are designed and introduced, and vendors are like, oh yeah, we have this, and then it's just not applied uniformly, which is kind of sad. Finally, you can see that equivalent size classes look promising, even though they tend to get larger as soon as you add more and more dependencies. Yeah, we also have some other interesting stuff in our paper, like we look at the extended control flow guard on Microsoft and how this basically works. We look a little bit at point authentication and the hardware-based Intel CET schemes. And you can also find our source code here in this repository. And with that, I'm concluding my talk, and I will be happy to take any questions.